This is not flatland. This is actually our world. And right here is our home, Earth. But why does it look so flat? Before the flat earthers out there start getting excited, I'm certainly not saying the Earth is flat. What I've done here is I've taken our 3D coordinate system and I've squashed it to make room for a fourth dimension, a W-axis. So every horizontal flat plane that we see in this representation of 4D space is actually a three-dimensional hyperplane. And our flat Earth is actually not so flat if we look at it in 3D space. But where exactly is this? Well, this is our reality, and as three-dimensional creatures, our W-coordinate is 0, just like the Z-coordinate of a flatlander is 0. So everything that we see and interact with in our world exists on this W equals 0 hyperplane. And so we will never be able to physically see what a four-dimensional object looks like, because all we will be able to see is a three-dimensional cross-section or slice of a 4D object as it passes through this hyperplane. This is actually the same problem that the flatlanders had. They can never physically see what a three-dimensional object looks like, only a slice as it passes through their two-dimensional plane. But don't get discouraged, because by studying these slices, it's possible to build an understanding of what 4D geometry looks like in a way that can supersede the need for direct visualization. So first, let's begin by looking at 4D objects from a more mathematical point of view. Consider the formulation of a circle. We can construct a circle algebraically using the Pythagorean theorem. And of course, we can change its location and size by changing its center coordinates and radius values. But that's only in 2 dimensions. In 3 dimensions, we have an additional z-axis to consider, and we account for this by using the Pythagorean theorem in 3 dimensions, which results in an additional z-squared term in our equation. In 4 dimensions, it's really not much different. By adding a w-squared term to our equation, we could transform our sphere into a 4-dimensional hypersphere. And we can use this equation to determine what a 3D slice would look like if this hypersphere were to pass through our world. Since everything that we see is on the W equals 0 hyperplane, let's substitute W equals 0 into our equation. Simplifying gives us this form, which we recognize as the equation for a sphere. So math tells us that 3D slices of a hypersphere are spheres, and the size of these spherical slices depend on the hyperplane's W0 coordinate in 4D space. So back to the representation of 4D space. We can draw our 4-dimensional hypersphere like this. And as it descends down the W-axis, eventually it intersects the W equals 0 hyperplane, where it enters our reality, allowing us to see a 3-dimensional slice. By watching the hypersphere pass through our world, we can visualize its geometry by watching how these 3D slices change. When a 3-dimensional sphere intersects flatland, it creates a growing and shrinking circle caused by the roundness of the sphere in the 3rd dimension. Flatlanders can compile these slices in their mind and visualize its 3-dimensional roundness by observing the rate of change of the radius. Similarly, as the hypersphere moves into and out of our world, it shows up as spheres that grow and shrink according to the curvature in the 4th dimension. So right now, by watching the morphing that's going on, we are actually, in our limited perception, seeing 4-dimensional roundness. Okay, so what would a hypercone look like if it were to pass through our world? Again, we can start by analyzing its algebraic formulation. By definition, the boundary of a 3D cone is formed from an extrusion of a circular base to a point in the z direction. And in 4D, the hypercone is an extrusion from a spherical base to a point in the w direction, which is also why it's sometimes referred to as the spherical cone. And of course, we will only see a slice given by the intersection with the w equals 0 hyperplane. And so our equation tells us that as long as the axis of the hypercone is aligned with the w-axis, each slice is a sphere whose radius depends on the w coordinate of the hypercone. So intersecting our world would look something like this. But what would we see if the hypercone rotated through four-dimensional space like this? Well, first, let's consider just a single arbitrary orientation. Obviously, this won't be a sphere since the slice is not aligned with the axis of the cone, but we can still figure out what this 3D slice looks like by reconstructing it piece by piece. Let's go ahead and break up the three-dimensional intersection region into two-dimensional pieces. Now remember, our equation tells us that slices taken along the axis of the hypercone are spheres. And so each piece is actually a two-dimensional portion of the three-dimensional spherical slice of the four-dimensional hypercone. So the object that we would see if the hypercone intersected our world at this angle would be the region that is being swept out by the red slices. Which in this case is something called a paraboloid, a 3D version of the parabola. This hypercone can also make other fun shapes. For example, consider this orientation. This 3D slice of the hypercone is an ellipsoid, a 3D version of the ellipse. Or how about the hyperboloid, a 3D version of the hyperbola? At this point, we should start seeing an interesting pattern here. If we take two-dimensional slices of a normal three-dimensional cone, we get things called conics. These include circles, ellipses, parabolas, and hyperbolas, depending on the angle that the cone is sliced. But if we take three-dimensional slices of a four-dimensional hypercone, we get the 3D analogs to these 2D conics, the spheres, ellipsoids, paraboloids, and hyperboloids. And the reason this happens is because of the hypercone's spherical symmetry around the w-axis. So to get back to the original question, a hypercone moving and rotating through four-dimensional space would look like a smooth morphing between the different 3D conic sections. And as long as it intersects our reality, we would see some pretty cool shapes that would certainly be unexplainable with only a three-dimensional worldview. Now I want to show you a four-dimensional hypercube. If you're a mathematician, you may know this by another name, the four-cube. Or if you've seen the movie Interstellar, you'd probably know it as the tesseract. So to construct a tesseract, we can start with a point and extrude it in the x direction to create a line. Then we can take that line and extrude it in the y direction to create a square. And then we can extrude that square in the z direction to make a cube. And finally, we extrude that cube perpendicular to itself in the w direction to make the tesseract. So, where a square has one-dimensional line boundaries, and a cube has two-dimensional square boundaries, a tesseract has three-dimensional cube boundaries called cells. In fact, there are exactly 8 cells that make up its boundary. So in order to determine what a three-dimensional slice of the hypercube looks like, we need to find the intersection of our hyperplane with each of the 8 cube cells that make up the tesseract's boundary. Since an intersection of a plane with a cube can only be a triangle, quadrilateral, pentagon, or a hexagon, we only need to find the points of intersection of the w=0 hyperplane with the edges of a single cube cell. Then we connect the dots to make a polygon, and repeat this for all 8 cells, and the polygons will come together to form a closed boundary that defines the three-dimensional slice. So this is a three-dimensional slice of our tesseract that is halfway intersecting our reality. And we can rotate it in any combination of the xy, xz, and yz planes as we can any other three-dimensional object. But nothing interesting happens. In fact, you're probably thinking that I'm lying to you, that this actually isn't a four-dimensional object at all. But the reason it looks so normal is because we are only rotating it in xyz space, meaning that the w coordinates of every point in the tesseract are not changing at all. It's kind of like a cube rotating in flatland. When rotations are restricted to only the XY flatland plane, the Z coordinates don't change, so it will always look like a square, and the flatlanders would agree that it looks pretty normal. However, in 4 dimensions, there are not 3 planes of rotation, but 6 planes, and the visuals get pretty interesting when we start rotating in the XW, YW, and ZW planes. So this is not exactly what we'd expect to see from a rotation. It's almost as if the hypercube is just stretching and contracting and magically changing colors. But let's see what's really going on behind the scenes. In a 2D world, if we looked at a cube rotating in the XZ plane, we would see the same stretching and contracting and color changes. But what's really happening isn't very magical, it's actually quite clear. The stretching and contracting is due to the fact that the diagonal is longer than the side length, and the color changes are just a result of edges of the cube rotating through the plane. For the tesseract, it's really the same thing but 1 dimension higher. The stretching and contracting is still from the diagonal being longer than the side length, but the sudden color changes on the faces are a result of entire faces of the tesseract rotating through our hyperplane. Things get even stranger when we start rotating around 2 planes. Again, we can make sense of what's happening by looking at the 2D case. The square distorts and magically grows 2 additional sides, but this is really due to the corners of the cube rotating through the plane. In 3D, the additional faces that we see are a result of edges of our tesseract rotating through our hyperplane. There's also a special subset of 2-plane rotations called double rotations, or Clifford displacements. And these are special because they represent rotations around 2 orthogonal planes, which is pretty cool considering this is impossible to do in only 3 dimensions. We can also rotate our tesseract in any 3 planes at once. And again, we can see a 2D analog of a 3-plane rotation to gain some insight into what we are seeing. We can also rotate around more than 3 planes at once. Additionally, we can learn more about the geometry of the tesseract by orienting it in certain ways and studying the 3D slices as we move it along the W-axis into and out of our world. We will be taking a look at the cases when the tesseract is oriented cell first, face first, edge first, and corner first. And to help understand and visualize what we see, before each of these cases I am going to show you the 2-dimensional flatland analog. And what we'll notice is that since the tesseract has 4 perpendicular edges coming out of each corner, and the cube only has 3, the 3D slices of the tesseract will look just like the 2D slices of the cube, except just 1 dimension higher. So here we go. Four-dimensional geometry is actually quite beautiful, partly due to its apparent complexity, but also because it's filled with mystery and otherworldliness. Because everything and everyone that we know live right here at W=0, our four-dimensional address. And as far as we know, no one can ever leave. We are confined, trapped even to this hyperplane. We are the flatlanders of a four-dimensional world, an infinitely thin, insignificant slice of something else's higher dimensional reality. Whether you find that comforting or chilling is up to you, but it opens the door to a very real question. What if our experience of the physical world is merely a representation of something extra-dimensional, and that our understanding of reality is limited to a three-dimensional interpretation that is inconsistent with actuality? Maybe there's a whole new world out there that we have yet to discover, a world that extends beyond into the fourth dimension. New space, new things, maybe even new life. But all of us here watching this video are the pioneers of this new place, the modern-day explorers from the history books, continuing the age-long search for answers to the mysteries of the world that we live in and the universe that surrounds it. Until next time. Hey guys, if you made it all the way to the end of this video, be sure to leave a comment and let me know what kind of four-dimensional stuff that you'd like to see covered in future videos of this series. After all, this is a series dedicated to exploring the fourth dimension, and I know a lot of you guys have some really cool insights and ideas to share. So I'm excited to read those in the comments down below. And anyway, thanks for watching, and I will see you guys next time.